so this is Unit 3. We are going to be talking about energy and work. Okay, so work has a defined property in terms of science that it doesn't have in real life. And so this is one of those words that, like volatile in chemistry, a lot of times we think of the word volatile as, oh, so Miss Bishop's so volatile, she just pops off at like the drop of a hat. Wiedemann Laws comes in here and touches her stuff and she loses it. Not wrong, but that's not what the word volatile actually means. It means to evaporate easily. It's not explosive. And so work is one of those things also. In order for something to do work, you have to move it a certain distance. So the definition of work is a force applied to an object over a certain distance. And so if you guys are doing any like stretching or anything for your sports or before you lift weights, do you do any of what are called isometric exercises? Do you know what that word means? It means like where you like lean up against a wall. You're not actually doing any work in the physical definition of the word because you're not moving anything. And so the only time you're doing work is if you're actually picking up your dumbbell or your weight or your kettlebell or whatever you're using. If you're not moving that weight a certain distance, you haven't done any work in the physical sense. Yeah.
So this it would be distance, not displacement, right? Or is it?
It depends on your frame of reference. So the formula for work is force is usually written like this. Oftentimes you'll also see it as this. This is the most basic form that the work equation takes. But if your force is not applied parallel to the surface, then you have to take the angle into account, and that's how we get this formula. Here, S is your displacement value. Some books, some people use X still. I almost always use X because I don't like inconsistency. It's one of the things that I have a hard time with physics. I have to turn my chemist brain off. Like chemists, we don't ever use two variables to describe the same thing. But in physics, we're like, oh, it's fine. Everybody knows what we mean. It's fine. And so it kind of drives me nuts a little bit. So I tend to use X. Just know that they are the same thing. Okay, so the unit for work, and now here's another W. So now we not only have weight as a W, but we also have work as a W. So context is really important. The unit for, I'll just use a different color here. The unit for work, if we're calculating work by finding the force, which is calculated in newtons, and we're multiplying that by some distance, n meters, your work unit then is what we call a Newton meter. But Newton meter has another name. It's abbreviated J, which stands for joule. Not like the Joule thingy, J-U-U-L or whatever. Aren't they bankrupt now? Aren't the Joules like no more? Anybody know about that?
I can only hope. I used to sum up my gas at the gas station I work at, but now we're done. So I don't even.
There's like a whole scandal with the joules. Okay, so that's your unit, a joule. Oftentimes we will use kilojoules. So to go from joules to kilojoules, you would. Anybody?
Divide by 1,000.
Yep. That's just a metric system knowing how to use. Okay, Okay, so now let's talk about, can I erase this? The work energy theorem. The work energy theorem says that if something is being moved a certain distance, moving means that it's in motion. And so if a thing is in motion, it has what kind of energy? Kinetic. And so therefore, isn't just the kinetic energy of an object the same as the work that's done on it? And that's what the work energy theorem is. If an object is in motion, it has kinetic energy, which I'm abbreviating capital KE, and which I will abbreviate now for always. If an object is in motion, it has kinetic energy. Therefore, this little triangle made of dots is the symbol for the word therefore. It's another thing that like your college professors will write on the board all the time, so you should know what that means. Therefore, work is equal to the change, the work done on an object is equal to the change in its kinetic energy. That is the statement for the work energy theorem. Okay, so what is kinetic energy then? What does that mean? Those of you who had physics last year maybe know what the formula for kinetic energy is. Do you remember? 1/2 m, so mass, times velocity squared. That's the regular formula for kinetic energy. So, if you're trying to figure out what change in kinetic energy is, that's kinetic energy final minus kinetic energy initial. So, therefore, work is equal to 1/2 mv final squared minus 1/2 mv initial squared. Now this might seem like a long formula. Don't worry, it gets worse. So every time we talk about different types of motion, we'll be talking about a different kind of energy. And we'll be talking about internal energy, which is the sum of all of the energies that an object has. There are 4 main ones that we'll be talking about: rotational, mechanical, potential, and then the spring energy. So this is just one bit of it. Yeah, look at somebody's formula sheet. Victor, can I look at yours quickly? Thank you very much. There's a really lovely preview of it. It's the last equation in Unit 6. And that's only one side of it, because that's only what it equals, not like what the change is in conservation of energy. We'll get to conservation of energy in a little bit, but not today. Okay, so here's what you need to know for the work energy theorem. Now, remember what you know about math. You can factor out things that are the same. And so you can say that this is also equal to 1/2 m times the subtraction of these two things, because the mass of your object doesn't change. That's a constant value. 1/2 is also the same. So if this is helpful, and in some cases it might be, other cases it won't. So just know what you know about math. Or I guess remember what you know about math. The last thing that I want to teach you today, and then we'll do some examples, is gravitational potential energy, or GPE. Okay, so what's potential energy? Yes. It's the energy, in physics we say it's the energy of position. And so an object at rest has the potential or the opportunity to do work. And if it's just at rest and nothing else is interacting with it, it has that opportunity to do work because of gravity. And so this is the mathematical formula. I must have said chemical. Oopsie. The formula for gravitational potential energy is simply mass times gravity times h, which is the height at which something is located. And remember that needs to be calculated in meters. Now, because of this, m times g is a force. M times g gives us the unit newtons. And so then the distance, the work that's done, is that force that's applied. Gravity is acting on it, and its mass, that together is the force, times the height at which the object is located. So the higher up an object is, the greater potential it has to do work, because it'll travel a farther distance. Does that make sense? So if you are at the top of a very high roller coaster, you have the potential, before you start going down, to do more work because you're up higher than if you were on like the little kid roller coasters, you know, that just barely leave the ground. Do you guys like roller coasters? Are any of you not roller coaster people?
When we went to Orlando or something, people made me go on them, and now I really like them.
Sometimes it's hard to like get over that like initial, like they're freaky. I'm really afraid of heights, and so, but I love roller coaster. Like I love doing it, but I have to psych myself up so much for it that it's a thing. Okay, so then, how would you calculate like the change, like the work done? It would be equal to mghf minus mgh naught. A lot of the times, one of those two h's is 0 based on your frame of reference. You can make the math easier for yourself. Any questions about that? Are any of those formulas on your blue sheet? I just can't remember. Some of them, like, some of these are a little simpler. You might find that you're able to memorize them. Especially before they get to be in the big conglomeration of internal energy.
They're on unit 4.
Oh, right. That's because it used. Yes, you're right. Thank you for noticing that. Unit 4 is now unit 3 because units 2 and 3 were pushed together, so that unit, like the next unit, would be, or so that they could add that other unit on fluids at the end. All right. So I wanted to do a couple examples from your book so that you know how to solve the problems, and then I'll give you your homework. Let's do number 14, 16, and 24. This is on page... Shoot, I don't know what page. Give me a second. 183, I think. Somewhere around 183. 14, 16, and something else. 24?
Is it the one where the strikes however kilograms in the ball?
I can't remember.
If the title of it is the work energy theorem and kinetic energy.
Yes, then you're right on.
It is on page 183.
Okie dokie. Okie dokie. Number 14. A golf club strikes a
And goes 30
point
times.
in order to launch it from the tee. For simplicity, assume that the average net force applied to the ball acts parallel to the ball's motion and has a magnitude of 6,800 newtons. Wow. And is in contact with the ball for a distance, I'm going to use x because that's what I want to do. This many meters. What speed does the ball leave the club? Okay, so we need to remember a couple of things. Work is equal to force times cosine theta times x. Now, if it's parallel, what would your theta be? Okay, do cosine of 0 and tell me what you get. Good. Okay, good. Okay, we know trigonometric properties. Well done, well done. Okay, so if that's the case, then you can eliminate that term. And so don't worry about the cosine then. Okay, so if we, what are we going to do with that though? We could calculate what the work is. And so we would get 68 joules. I suppose I should show my work. 6,800 newtons times 0.010 meters. And so I can do that math in my head because it's just dividing by 100.
68.
And then that's not the answer we're looking for. So how would we find speed? Well, if we remember that work equals 1/2 mass v squared, we can solve this formula now for velocity. So velocity is equal to square root of 2w divided by m. Now, if you don't want to solve for work first, you don't have to. You can do algebra. This is probably what I did when I did this problem. It helps if you put the right examples in your notes from the right chapter. Did I do something wrong?
I don't think so. It's 68, right?
I think so,
Okay.
but don't quote
I
me.
thought you said 6 point.
Oh, I might have.
That's right.
I might have, absolutely. Just at the beginning of class, I started developing an ocular migraine, and so I apologize. It's gonna be a rough rest of the day.
Dude, all the teachers are having bad days today. Mr. Olson wasn't having a good day.
This blizzard was kind of bad.
Mr. Erickson was having a bad day.
Oh, I
I
heard
think we
this.
should just go home. Like
Yes,
today. Call it a
yep.
day.
Can't do anything more.
Was he mad for you guys, right?
What?
You didn't, I heard you said a word out. Well, no. We had like a work day and stuff, so.
All right, mathing. I got 54
Yep.
or 55, I guess. I'm too late. Oh. So, what's your unit?
Meters per second.
Good. So we have to know two things here. We have to know how to calculate work and then how to turn work into kinetic energy. You could have done 1/2 mv squared equals force cosine theta times x and started with that if you wanted to, but that's up to you.
And then just solve for V not there.
Yep. Yep. All right, I'm going to clear this. Let's do 16 and see how that goes. 16 says, starting from rest, a 1.9 times 10 to the minus 4 kilogram flea. Oh, what fun! A flea.
Did that one Christmas.
Oh, what fun it is to jingle bells. Little one horse open sleigh. Okay,
Okay, so you should go over.
dashing through the snow. And okay, so while the flea is pushing off the ground, it exerts an average upward force of 0.38 newtons. This force does blah 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 kind of work on the flea. So positive 2.4 times 10 to the minus 4. I'm so happy that they asked us to use these scientific notation numbers. What is the speed of the flea when it leaves the ground? So A would be V final equals question mark. And then B, how far upward does the flea move? What would you be solving for in part B? X. Okay, so let's see. A couple of things that we know. I think work equals force times cosine theta x. I think you could actually solve for that first, right? I mean, because you have all the information. You've got work done, you've got a force, and so you can solve for x. W divided by force. We're assuming that we're not at an angle. And so that would be some nice and easy, oops, not to the minus 14. Some nice and easy math here. Whatever you get for an answer.
Wait, what are you trying to find out?
I thought about doing B first, just because I think it's easier.
Oh.
But it doesn't really matter. Work is equal to delta KE, and that is equal to 1/2 mass V final squared minus 1/2 MV naught squared. But this whole nonsense is equal to 0. So maybe I don't need to write that. But I do still need to solve for velocity final. And so that's going to be the same equation that I just used. So 2W divided by N. And that's how I'll calculate V final. Oh. Somehow I typed a random cosine in there. So I get 6.3 times 10 to the minus 4. What's your unit for part B?
Meters.
Good. And then 2 times 2.4. What's for lunch today?
Chicken nuggets.
Oh. Oh. And then I got 1.59 meters per second. Is that what y'all got?
Yes.
All right, good. Anybody have any further questions about this? How did this go?
Pretty good.
Easy? Okay. Let me give you your homework questions then. I was gonna do 24, but my head hurts. This I think is homework 16. So you're on page 183, 184. You're gonna do numbers 10, 11, 15, 19, 25, 26, and 27. Don't worry, they're all easy.
I know. I mean, she's she knows what the like.
Oh, it's all just easy.
But
We had a phone.
It's time to play.
there are a bunch of missing MCQs out in AP College land. Get them in. I graded those.
Yay!
So get your MCQs done. Does everybody have this written down now?
Yeah.
Okay. I want to disconnect my computadora here.
Number 10. Coefficient. Number 15. What was it? Man does something on the flame to not being allowed to smoke. Yeah. Man urinates on so it has to get Oh, you're better than
Yeah, go ahead.
coefficient kinetic friction.
You see the Raptors court?
Yeah.
Oh, determine the
Cool.
Oh,